So let's do some calculations related to the pH of a strong acid or base solution. So remember, the strong acids and bases dissociate completely, and there are 6 strong acids and 6 strong bases that we just memorize. We know their identities. And so if we're calculating the pH of a strong acid or a strong base, we can use stoichiometry to determine the H3O plus concentration. Because the acid or base dissociates completely, the reaction functionally is so far to the product side that we don't need to account for equilibrium. So that means that the H3O plus concentration will equal the initial acid concentration, or the OH minus concentration will equal the initial base concentration. So let's see how this works. What is the pH of a solution containing the strong acid HCl at a concentration of 3.5 times 10 to the minus third molar? Okay, so we said that HCl is a strong acid, so in water it will dissociate completely to the products to form H3O plus and chloride ion, the conjugate base. So if we're trying to find the pH, then the pH is going to be the negative log of the H3O plus concentration. So to find the H3O plus concentration, we can take that 3.5 times 10 to the minus third molar HCl, and we know that there is 1 mole of H3O plus for every 1 mole of HCl, so that the concentration of H3O plus will be the same, 3.5 times 10 to the minus third molar. Now, if we put that into our pH formula, pH equals negative log of 3.5 times 10 to the minus third molar, then we get that the pH of this solution equals 2.46. Okay, let's think about that number. That number is consistent with this being an acidic solution, so because it's less than 7. It also is consistent with this concentration, because this 2.5 is pretty close to the exponent negative 3, or the value of that, the 3. Okay, so let's try this one. What would be the pH of a solution of 3.5 times 10 to the minus third molar strontium hydroxide? Strontium hydroxide is a strong base, so it will dissociate completely into strontium ions and hydroxide ions. Now, if we want to calculate the pH of this solution, we need the negative log of the H3O plus concentration. But H3O plus isn't in our reaction, so instead we're going to need to use the autoionization of water to help us interconvert between OH minus and H3O plus. So we can use the fact that in water, the product of the H3O plus and OH minus in solution will equal Kw, which at 25 degrees, and we'll assume, unless we're told otherwise, that we're at 25 degrees, is 1 times 10 to the minus 14. Okay, so if we can find the OH minus concentration, we can get to the H3O plus concentration and thus calculate pH. So here we have 3.5 times 10 to the minus third molar strontium hydroxide. We see here that in our stoichiometry there are 2 moles of OH minus for every 1 mole of strontium hydroxide. So that means that our concentration of hydroxide in this solution will be 7.0 times 10 to the minus third molar. And we can use stoichiometry here because we know that strontium hydroxide is one of our strong bases. Okay, so now we need to solve for the OH minus, or we know the OH minus concentration. We need to solve for the H3O plus concentration, which if we rearrange the Kw formula is going to be Kw divided by OH minus. So that will be 10 to the minus 14 divided by the OH minus we just found, 7 times 10 to the minus third. All right, that will make our H3O plus concentration equal 1.4, 3 times 10 to the minus 12 molar. All right, and then if we take negative log of the H3O plus concentration, 1.43 times 10 to the minus 12, we get that the pH of the solution is 11.84. So does this number make sense? I think so. This solution is basic, and that is consistent with this being a strong base. We also see that our pH value close to 12 is similar to the value of our exponent on our H3O plus concentration. But what if we want to go the other way? The pH of your coffee solution is probably something like 4.95. And so how can we find the H3O plus concentration? So we know that pH equals negative log of H3O plus. And if we want to solve for the H3O plus concentration, we need to get it out of the log. So how do we get rid of a log? So if you have log of x and you raise it to so 10 to the power of log x will equal x. So we need to raise both sides of our equation to the power of 10. Okay, so that's going to be 10 to the power of pH equals negative H3O plus concentration. And actually, it would be easier if we got H3O plus all by itself. So if we divide both sides by negative 1, then we actually end up with that H3O plus equals 10 to the negative pH. All right, so here we can calculate H3O plus equals 10 to the negative 4.95, which, if we put that into our calculator, we get that a value of 1.1 times 10 to the negative 5. Does that make sense? Well, our exponent is less than 10 to the minus 7, so that's consistent with this being an acidic solution. And also, we see that our exponent, minus 5, is close to the pH, close to 5. Okay, how about this one? Your bleach solution has a pH of 11.5. What's the OH minus concentration? So once again, we know that pH equals negative log of the H3O plus concentration. And so if we want to, from pH, we can find H3O plus concentration, but if we want to find the OH minus concentration, we're going to have to use Kw again to convert between H3O plus and OH minus. And we know that the Kw we can assume this is 25 degrees, is 10 to the minus 14. Okay, so we said that the H3O plus concentration, if we rearrange the equation, is going to be 10 to the negative pH, or in this case, 10 to the negative 11.5. Our H3O plus concentration is thus going to be 8.91 times 10 to the minus 12. Okay, and now we can rearrange our Kw expression to solve for OH minus. So OH minus will be Kw divided by H3O plus, which will equal 10 to the minus 14 divided by 8.91 times 10 to the minus 12. And I get that to be 0.00112 molar. Or if you put that in scientific notation, that would be 1.12 times 10 to the minus third. And that will be our OH minus concentration. Okay, so we've done several calculations here, manipulating pH and H3O plus and OH minus concentration. And so together, these represent a kind of toolkit for you to be able to get to the quantity that you want.